So in terms of molecular simulation, there's really three key things you can do with it, which is exciting. One is, I think of as a computational microscope, right? So the idea is you just directly see what's happening. So you can make a movie and see what the atoms are doing. This is a very powerful and useful tool because it gives us access to a temporal and spatial scale we haven't had access to previously, particularly the nanoscale, right? Like nanometers, nanoseconds, kind of a billionth of a meter, a billionth of a second. Very hard to do it experimentally because these things are much smaller, they're atom sized, right? So you need something similar size to kind of observe them experimentally, but we can potentially get at it computationally, which is exciting. And Amelie, your previous guest, talked about this in the protein folding context, right? What we're really interested in now is how do they move? What are their dynamics? And particularly, at these very short time scales, which we can't get to experimentally below, a microsecond. And that's where these techniques are really useful. And so the hope is that if you can simulate a ton of things, you start to make important and new discoveries and find new things out just by looking at them, right? Which is very exciting. The second one you can do is in silico experiments, right? So you don't now have to go and order the chemicals and synthesize the new molecule and do all this work to try and then see it in action and then use microscopy to try and understand what's happening. You can just change the atom type in your input file and rerun the simulation, right? So you could do simulations much more quickly, hopefully, than you could do them experimentally. Eventually, you could think about doing high throughput things with this, right? So trying thousands of simulations and just trying to brute force find out which material works best. The third thing you could do is actually use those simulations to extract data for larger scale models. Think of this as providing a bedrock for physical simulation, right? So we simulate all sorts of physical systems, the climate, rockets, whatever. You simulate these things with all sorts of modeling approaches, but these all need to be parameterized, right? They need to have numbers plugged into them. And it's often very hard to work out what those numbers should be. You have to do experiments, very hard to do those often. Whereas if you could use lower scale simulation to extract that information, you could plug it into these models, which would be very useful. And then the other thing you could do is you could generate training data sets this way, which you could then go and train your generative models on, which would be great as well. And then there's also this coarse graining thing I've mentioned, which is what I was doing with the crystallization. And so one day you could think about simulating how proteins fold with time. And in fact, people are already starting to do this using some of the approaches that Amelie was talking about, training on all atom molecular dynamic simulations to then enable you to look at how proteins fold dynamically, which is very exciting.